Hi folks, this is an explanation about buckling. And so if you recall from class, we were looking at this problem where we had the triangular member and then linkage 2, and we're looking for the buckling factor of safety in linkage 2. And so we went through and we solved for the two force the force in the two force member, right, link 2. We found that force FBD, and then we also found the stress there. But what was more important was rather identifying the critical force rather in that member. And so from the givens, we can calculate the length of the linkage, the inertia, the area moment of inertia, the cross-sectional area, and then what we looked at was this radius of gyration here. And so the radius of gyration is the square root of the area moment of inertia divided by the area. And so that gives us an alternate way of describing those pieces. You might recall a mass moment of inertia and radius of gyration in dynamics. This is similar, but instead uses the area moments of inertia. In order to solve for buckling, we also need to know the yield strength, the modulus, and then the constant that corrects for the end conditions. And so there's a table for that, table 4.2. And so we can then find the slenderness for the critical point, calculate the slenderness for the in-plane or out-of-plane buckling that we have, and then choose between using the Johnson or Euler curves. So Johnson curves are used for less slender linkages or links, and so that's when the actual slenderness ratio is less than the critical slenderness ratio. Euler is used for slender columns, and that's when the slenderness ratio exceeds the critical ratio. And so we can find the critical slenderness ratio using the constant for the end condition, the modulus of elasticity, and the strength. And the actual slenderness ratio is the length of the link divided by its radius of gyration. And at that point, then we find the critical force or the critical load that causes buckling based on either Johnson or Euler, and then the safety factor is the critical load over the applied load. And so when we look at the Euler curve, the critical load is the correction or the constant. It uses the modulus of elasticity, and it uses the slenderness ratio squared. And so that's equation 444 for Euler buckling. And I forgot to note this equation, but it should be in a similar place, so something close to that here. The critical load, and I believe I'm actually missing a term. I believe there is an area here, and so we'll go confirm that. I think this is the critical load over area is this, and so it should have an area on this side. And so here we have the yield strength. This is the slenderness ratio. And so this is the expression for critical load in the Johnson portion of the curve. These are not competing, but rather different areas of interest. So Euler curves, this only works for slender rods. So this only works if the slenderness ratio is higher than critical. And the Johnson only works when the slenderness ratio is less than the critical. So, and so number 9 on the homework was looking for the in-plane factor of safety, and number 10 was looking for the out-of-plane factor of safety, which is why that's noted that way. So to look at it within the text's slides here, right? So this is what the curve looks like, and this portion here is the Euler curve, which is more slender than the critical slenderness ratio, and this portion here is the Johnson curve, which is less slender than that critical slenderness ratio. And so on the Euler curve, we see that, so they call it the unit load, the critical load over the area. And so when I'm looking for critical load, I just multiply by the area. And so that's equation 444. And then as the equation gets shorter, we have these intermediate length columns. And so this is where we use the Johnson formula or parabolic formula. And so we have this alternate curve that describes the critical load for this less than the critical slenderness ratio portion here.